Now we will start the theorem number 2. Theorem number 2. And the theorem is, if my function f is a function from a to b, and if x is a subset of b and y is also a subset of b, then we have to prove that what is the inverse image? The inverse image of x union y must be equals to the inverse image of x union the inverse image of y. So we have to prove this. So I already said how to prove this kind of equals of two sets. Okay. So in other words, the inverse image of the union of two sets is the union of their inverse images. Sometimes in words also they may ask the question. The inverse image of union of two sets is equals to the union of the inverse images. We have to prove it. Now, first we will prove that this one, the left hand side, is a subset of the right hand side. So let us take one element from the left hand side set. So let A belongs to this one, F inverse of x union y. So before the student must be very much have good knowledge in what is inverse function, what is inverse image, what is pre-image, everything, the definitions they need to be thorough. Okay, they should be knowing the definition before reading this theory. So first I take one element from the left hand side set. So if A belongs to the inverse image of x union y, then my f of A must belongs to what? X union. This is the thing. So if f of A belongs to x union y implies what? If an element belongs to the union of two sets, so what is the definition of union of two sets? Then f of A belongs to x, or my f of A belongs to y. Okay. So which implies, so again, if f of A belongs to x, then my A belongs to what? F inverse of x. Or here, if f of A belongs to y, my A must belongs to what? F inverse of x. So my A belongs to, this is also a set, all the inverse images belongs to the domain. That's important. This A belongs to inverse image of x, or A belongs to inverse image of, here y. Inverse image of y. So as per the definition of union of two sets, we can say that this belongs to f inverse of x union f inverse of y. So what we have proved? We have taken one element from the left hand side set, and we finally try to prove that it belongs to what? Right hand side. So an arbitrary element or general element belonging to this set also belong to this set. So what you can conclude? So every element of this set also belongs to this set. So what is the meaning? This concludes that therefore this set is a subset of this set. That's all. Therefore f inverse of x union y is a subset of f inverse of x union f inverse of y. I name this as the first result. So now I have to prove the other way. This one is a subset of this set. So we are going to take one element from the right hand side set. That's the next thing. Conversely, if we take one element from the right hand side, f and b is element of f inverse of x union f inverse of y, then so what's the meaning? It's a union of two This is one set, this is the other set. If B is a union of two sets, then B is an element of the first set, B is an element of the first set, or B is an element of the second set, that is called F inverse of, which implies if B is element of the inverse image of X, then my F of B must belong to what? X. Or here my F of B must belongs to same thing. So F of B is an element belongs to X as well as or Y, then this F of B belongs to X union Y. If F of B belongs to X union Y, then my B belongs to F inverse of X union Y. Okay, so thus B belongs to F inverse of. So what we concluded, we took one element from this set and finally proved that it also belongs to this set. So what do we conclude? Therefore, F inverse of X union F inverse of Y is a subset of F inverse of X union Y. This is true. So what you can conclude from 1 and 2, this is a subset of this, and this is a subset of F inverse of X union Y. So from 1 and 2, what you can conclude? From 1 and 2, we get the result. That is, F inverse of X union Y equals to F inverse of X union F inverse of Y. Hence the theorem. Okay, we completed the theorem. This is the result is proved. Now we go to the next result. Here, just imagine this is my set A and this is my set B codomain. Our function is mapping from here to here, and what is the other things given? X is a subset of B, something like this, and Y is also a subset of B. Maybe they intersect. We think that they intersect. Y is also a subset of B. So we proved it. So what is X union Y? This is X union Y. Okay, this is X union Y. So what is F inverse of X union Y? So what are the pre-images of the every element in this set? Okay, every element in this set, there are a lot of pre-images are there. That set we call it as what? F inverse of X union Y. F inverse of X union. So what is F inverse of X? Suppose X alone is there. For that you find the what? Inverse image. Then F inverse of Y separately somewhere here. What we have proved it, the union of these two sets is equals to F inverse of X union Y. For example, this is okay. Suppose this is X alone. First I concentrate on X alone. This is B codomain. This is the domain. My F is a function from A to B. And suppose we take only X alone because X is a subset of B. And what are the pre-images of this set? All the elements will have pre-images. Some element may not have any pre-image. That we don't mind. So many elements are there. And this set, whatever the pre-images, we call it as what? F inverse of X. Okay. Similarly, suppose it may intersect, Y may intersect. Suppose I take Y is not intersecting. So just clearly view what is Y. This is my Y, and there will be pre-images for this set. I think something like this. I call this set as what? f inverse of y. So what we have to prove is, so f inverse of x, this is f inverse of x and this is f inverse of y. F inverse of x union f inverse of y must be equal to, suppose you union these two sets and totally I will be getting f inverse of x union y. That we are going to equate that f inverse of x union y equals to f inverse of x in union f inverse of y. That's what we have proved it. So you must know where is x, what is inverse image, where it falls. So for that only I have given some outline. This is not required for writing the proof. Okay, because we are studying abstract subject. It's everything we have to denote by proof. No maximum, no geometrical significance is used. Okay, we can visualize it for our better understanding, but maximum we have to use theorems and proofs without any geometrical influence. Okay, so this is a theorem number 2, I think. This is theorem number 2. You make it a continuous numbering. Theorem number 2. Next, theorem number 3. Same like this. So now same like this is for intersection. Intersection. That is, if f is a function from a to b and if x is a subset of b, and same like the previous theorem, b is subset of b, then my f inverse of x intersection y must be equals to f inverse of x intersection f inverse of y. Same thing, same like the previous thing, but here there is union, here it is intersection. Now let us assume that, let's take one element from this set. Let a belongs to f inverse of x intersection y. See, to be very much you must know what is happening. Simply we cannot memorize everything. Suppose this is a and this is b, and so what we have taken is a element of, suppose I take this is x intersection y. So if a, so the inverse image of this under the mapping f will fall a. What are the pre-images? Something like this. Here I say, suppose this is my f inverse of x intersection y. All the pre-images. Okay. Suppose I say one element a belongs to what? This inverse image of f inverse of x intersection y. Something like this. Suppose a is here. So what happens is, definitely the image of this a will fall here only. This is f of a. F of a will be inside this. It won't fall outside. If it is falling outside, this a won't be inside inverse image of x intersection. So that's why if a belongs to f inverse of x intersection y, then my f of a must belong to what? X intersection. This is what we have written. So if f of a belongs to intersection of two sets, so what's the meaning? F of a belongs to x, you have to use the word and f of a belongs to y. Now my f of a belongs to x and f of a belongs to y implies my a must belong to what? F inverse of x, and my a belongs to f inverse of y. Same thing. Suppose same like this, you can see just this is the beginning, that's why I am explaining more. Suppose this is a, this is b, and what way is this taken? F of a belongs to x. Suppose this is my x, this is my, suppose f of a. If f of a belongs to x, so definitely the pre-image of this will be present. There will be many pre-images, who knows? There will be many pre-images, we don't know about this. There will be many pre-images. Okay. Maybe many pre-images that is lying outside f inverse of x. So definitely suppose A is belonging to X, then definitely f of A belongs to X, then its pre-image, that is A, must belong to what? This should be what? F inverse of X, definitely. Maybe some will be outside F inverse of X, but the inverse image of this element will be what? Inside F inverse of X. Okay, so that's what is given here. A is element of F inverse of X, and A is also belongs to F inverse of Y. So it's belonging to two sets. So A belongs to F inverse of X intersection F inverse of Y. So we have proved the first part. So we taken one element from the left hand side set. Finally we proved that that element belongs to the right hand side set. Now again the same thing the other way. Conversely, if suppose I take B is element of F inverse of X intersection F inverse of Y, then what is the meaning of this? B is an element of F inverse of X and my B belongs to F inverse of Y. If B belongs to F inverse of X, then my F of B is an element of X and my F of B belongs to Y. It belongs to both X and Y, so F of B belongs to both X intersection. If F of B belongs to X intersection Y, so what is the meaning? Which implies B is an element of F inverse of X intersection Y. So what we have proved is, we took one element from this set and tried to prove that, finally we proved that it belongs to the same set. Therefore, our F inverse of X intersection F inverse of Y is a subset of F inverse of X intersection Y. This is the second part. So from 1 and 2, that is, therefore, here I forgot to write it step. Therefore, F inverse of X intersection Y is a subset of F inverse of X intersection F inverse of Y. This is the first part. So from 1 and 2 we get, from 1 and 2 we get F inverse of X intersection Y equals to F inverse of X intersection F inverse of Y. Hence the